Orbits happen because of gravity. The force of gravity on an object near the Earth is proportional to the mass of the Earth divided by the distance between the object and the center of the Earth squared. If an object is twice as far away from the center of the Earth, it experiences 1/4 as much gravity. As a consequence of this inverse square law, an orbit can only take the shape of a conic section, that is to say, a slice out of the middle of a cone at some angle. There are only 4 possible shapes that can result: a circle, an ellipse, a parabola, or a hyperbola. Now, these last 2 shapes, the parabola and the hyperbola, are escape trajectories. They represent the object leaving the Earth and never coming back. We can pretty much ignore them. They're not very interesting. We're interested in the orbits where an object keeps going around and around and around the Earth over and over again. That means either a circle or an ellipse. Now, in a circular orbit, the center of the Earth is at the center of the circle. Well, okay, that's not quite true. The center of the circle is where the center of mass of the two-body system is. In the Earth-Moon system, for example, the center of mass is inside the Earth, but isn't exactly at the center. It's somewhere between the center and the surface of the Earth. But with a small object orbiting the Earth, like the International Space Station, the center of mass is so close to the center of the Earth as not to make any difference. So let's just call it the center of the Earth and save ourselves some trouble. Now, while circular orbits do exist, they're rare. It's hard to get an orbit to be exactly circular. It's usually going to be at least a little bit elongated or eccentric. So, by and large, almost all the orbits you're going to encounter are going to be ellipses. In an elliptical orbit, the Earth isn't at the center of the ellipse. It's off to one side, at one of the ellipse's 2 focus points. Now, there's a precise geometric definition to what the 2 focus points, or foci, are, involving line segments that add up to the same length, and reflections off the inner surface, and a directrix, and blah blah blah. All you really need to know about the 2 foci is that they get farther and farther apart the more elongated or eccentric the ellipse becomes, and if you draw a line through the 2 foci, the points at which this line intersects the ellipse are going to be the shortest distance of any point on the ellipse to one focus and the longest distance of any point on the ellipse to the other focus. And this holds true for both points on the ellipse. Both of them are the shortest distance to the near focus and the farthest distance from the other focus. And by the way, that line segment going all the way through the middle of the ellipse, through the 2 foci, and touching the ellipse on both sides, is called the major axis. If you cut it in half so that it only goes out to the center of the ellipse and stops, it's called the semi-major axis, because it's half the length of the major axis. Remember this semi-major axis. It's going to be important later. Now, in an elliptical orbit around the Earth, the center of the Earth is at one of these 2 focus points. What's at the other focus point? Well, nothing really. It's just a mathematical curiosity. So let's ignore the other focus point. It's not important. Now, as it turns out, there's a special name for an object in orbit. It's called a satellite. And that word isn't just restricted to the artificial satellites we humans have launched into Earth orbit that relay radio signals, or that take pictures of the Earth, or that are important for GPS. All objects that orbit the Earth are satellites of the Earth. The International Space Station is a satellite. The Moon is a satellite. Little pieces of space debris knocked loose from the asteroid belt that get captured by the Earth's gravity are satellites. If it's orbiting the Earth, it's a satellite of the Earth. As a satellite moves through its orbit, it gets progressively closer and closer to the Earth until finally it reaches the point at which it's the closest to the Earth. That point of closest approach is called perigee. The point on the opposite side of the orbit, where the satellite is farthest from the Earth, is called apogee. If the satellite's orbiting something other than the Earth, these points are called something else. Periselene, perijove, pericytherion, periarion, perihelion, periastron, perigalacticon. The generic term for these points in an orbit around an arbitrary object are periapsis and apoapsis. But this video is primarily concerned with Earth orbits, so let's just focus on perigee and apogee. Focus. Like the focus points in an ellipse. I made a funny. Now, a satellite doesn't just change its distance from the Earth as it goes around, it also changes its speed. It gets faster and faster until it's going the fastest when it reaches perigee, and then it slows back down until when it reaches apogee it's going the slowest. Why? For the same reason that a baseball thrown into the air will get slower and slower as it goes higher and higher, and then, as it falls back toward the Earth, will go faster and faster as it gets lower. An object orbiting the Earth is in freefall. This is why astronauts aboard the International Space Station appear to be weightless. They're in a low Earth orbit, so the Earth is actually pulling on them with 4/5 as much gravity as it would if they were standing on the ground. But because they're orbiting, they are in free fall, so they're not experiencing that gravity as weight. So with all this changing speed and changing distance over the course of a satellite's orbit around the Earth, how long does it take the satellite to go around the Earth once? What's the orbital period of the satellite? Well, as it turns out, there's a pretty straightforward relationship between the size of an orbit and its orbital period. This relationship was discovered by Johannes Kepler in 1619 for planets orbiting the Sun. Then Sir Isaac Newton came along later and generalized this for all orbits. The square of the period multiplied by the sum of the masses of the two objects, the object being orbited and the satellite doing the orbiting, is equal to a proportionality constant times the cube of the orbit's semi-major axis. Remember the semi-major axis? I told you it would be important. That's the A in this equation. Unfortunately, if you want to solve the equation for the period, you've got to do a little bit of algebra. You need to divide both sides by the sum of the masses and then take the square root. But once you've done that, all you have to do is plug the numbers in on your calculator, a scientific calculator that can do cubes and square roots, and bingo, you've got the period. Okay, let's take a real-world example of an orbit so we can see all these numbers in action. Sputnik 1, the very first object placed in Earth orbit by human beings. It was put in orbit by the Soviet Union in 1957. Now here I face a little conundrum. If I start quoting distances in miles or feet, then I'm an old fuddy-duddy who hasn't embraced the metric system like the rest of the world has. And I also run the risk of confusion between statute miles and nautical miles, both of which have been used by NASA on space missions in the past. On the other hand, if I start quoting distances in meters or kilometers, then I risk alienating the American audience who's used to hearing about things in miles and feet. So, I'm gonna do neither. I'm gonna give all of the distances in the rest of this video in furlongs. 1 furlong is 1/8 of a statute mile, or 660 feet, or 201.17 meters, or 1.245 times 10 to the 37th Planck lengths. Furlongs are still used in horse racing, and Tolkien used furlongs in The Lord of the Rings for distances shorter than a league. Yeah, okay, we get it. When the Soviets launched Sputnik 1 in 1957, Its launch vehicle, the rocket booster that pushed it into orbit, accelerated it faster and faster and pushed it higher and higher until finally, when the rocket ran out of fuel, Sputnik 1 had achieved its perigee altitude of a little more than 1,100 furlongs above the Earth's surface. That might sound like a lot, but remember the Earth is over 63,000 furlongs across, so 1,100 furlongs is actually a pretty low altitude for a space vehicle. Its orbital speed when it reached perigee was 38.6 furlongs per second. To put that speed into perspective, a .357 Magnum bullet fired from this gun will be traveling a little faster than 2.5 furlongs per second. That means Sputnik 1, when it was launched and when it entered perigee, was moving at nearly 15 times the speed of a bullet fired from this gun. At that speed, its apogee altitude on the opposite side of its orbit was a little more than 4,700 furlongs above the Earth's surface. The Soviets were actually aiming for an apogee altitude of 7,200 furlongs, but they couldn't get it going fast enough to reach that high. It was the first artificial satellite ever. You couldn't really expect everything to go perfectly. So, with an apogee altitude of 4,700 furlongs, a perigee altitude of 1,100 furlongs, and an Earth in between them of 63,000 furlongs, what was Sputnik 1's orbital period? How long did it take Sputnik 1 to go around the Earth once? Well, if you add all these distances together, you've basically got the major axis of the ellipse, which is going to be a little over 69,000 furlongs. This means the semi-major axis is about 34,500 furlongs. And as you doubtlessly recall, our formula for the period is the square root of the conversion constant times the cube of the semi-major axis divided by the sum of the masses. The semi-major axis, A, is 34,500 furlongs. This means A cubed is A times A times A, which works out to 4.1 times 10 to the 13th cubic furlongs. If you're not familiar with scientific notation, now's the time to start. That times 10 to the 13th part means to take the decimal point and move it to the right 13 places. So 4.1 times 10 to the 13th is 41 trillion. To enter this number on a scientific calculator, you would type 4.1, then hit the exp key, then type 13. To enter this number in a spreadsheet or in the source code for a computer program, you'd type 4.1E13. They all mean the same thing. So our A cubed term is 4.1 times 10 to the 13th, or 41 trillion cubic furlongs. Now the mass of the satellite, that lowercase m term in the denominator, if we were dealing with a big satellite like the Moon, we'd have to worry about it. But with a satellite as small as Sputnik 1, we can pretty much ignore it. The mass of the Earth plus the mass of that tiny little satellite is going to be just about the same as the mass of the Earth. This reduces the equation to just the square root of Ka cubed over the mass of the Earth, which should be easier to work with. Now K, that conversion constant in the numerator, turns out to be 4 pi squared over Newton's gravitational constant, which in our units works out to, and I'm not kidding here, 8.064 times 10 to the minus 7th Earth mass seconds squared per cubic furlong. So, plugging all these numbers into the equation, we get that the period of the orbit equals the square root of 8.064 times 10 to the minus 7th Earth mass seconds squared per cubic furlong times 4.1 times 10 to the 13th cubic furlongs, all divided by the mass of the Earth. But hey, guess what? Those cubic furlongs per cubic furlong, they cancel each other out. The mass of the Earth cancels each other out too, so we don't even have to bother looking up the Earth's mass. because the equation now reduces to the square root of 8.064 times 10 to the minus 7th seconds squared times 4.1 times 10 to the 13th. Plug those numbers into your scientific calculator, multiply them together, and take the square root, and we get a period of 5,750 seconds, or about 96 minutes. If you look up the actual historical record for Sputnik 1, you'll get a period of 96.2 minutes. And that's because we were doing a little bit of rounding off here and there, so we weren't going to arrive at an exact answer. But it's pretty close.
Now suppose you want to change an orbit. Suppose you want to maybe change your perigee altitude, or your apogee altitude, or you want to change the angle of inclination that your orbit has with respect to the Earth's equator. Well, these kinds of things are a much more complicated topic, known as astrodynamics.
It involves rotation matrices and reverse calculation and complete parameterization of the 6 Keplerian elements and approximating the bulge of the Earth as a belt of material and ground tracks and deriving orbits from ground observations and the Tsiolkovsky equation and Hohmann transfers.
Astrodynamics is a pretty big field of physics and engineering. There are even people that do it for a living. They're called rocket scientists. But guess what? By getting this far through this video, you've already been exposed to a little bit of rocket science. Most of rocket science is just dealing with orbits. Compared to some other fields of physics, like quantum mechanics, the mathematics isn't even that complicated in rocket science. Rocket science has an undeserved reputation for being something super hard and something no one can get their mind around. It's not that hard to get your mind around it. And if humanity is ever going to get serious about leaving the Earth and branching out into the solar system, we're all going to need to be familiar with rocket science.